Acetaminophen. Acetaminophen is a synthetically occurring analgesic and is most commonly known as a major component in Tylenol. It is therapeutically used for the relief of fever, headaches, and minor aches and pains. Acetaminophen is a white crystalline powder purchased over the counters at almost all stores in the form of pills, capsules, or liquids. Therefore, oral ingestion is the most prominent route of exposure. Acetaminophen is the leading cause of drug-induced liver failure in the United States. Overdoses are common and can be potentially fatal. Absorption of acetaminophen happens rapidly and almost completely. The log POW value is between 0.51 and 0.91, within the drug-like range, and therefore can be absorbed through oral ingestion. The functional groups on acetaminophen are acetamido, which is a very polar and hydrophilic functional group, as well as an alcohol, which is a fairly polar and hydrophilic functional group. The pKa of the strongest acidic proton is 9.46, therefore the physiological charge of acetaminophen is 0. The absorption of oral acetaminophen occurs primarily along the small intestine in the enterocyte by passive diffusion. The rate-limiting step is the rate of gastric emptying into the intestines. Once absorbed, acetaminophen continues through the villi interstitial fluid, past the vascular membrane of the GI, and to the villi capillaries. Once here, acetaminophen can travel through the hepatic portal vein into the liver sinusoid and the hepatic epithelium. It then gets absorbed into the hepatocytes and thus making its way through multiple barriers to its target cell. Through this process, approximately 25% of the dose of acetaminophen partakes in protein binding and is kept out of circulation. Acetaminophen is metabolized primarily in the liver, where most of it is converted to inactive compounds. 45 to 55% of the dose of acetaminophen undergoes glucuronidation. This process is facilitated by different UTG enzymes in the liver or in the gut. Also, 35% of the acetaminophen undergoes sulfation. Acetaminophen is biotransformed using multiple enzymes and enzyme systems. For example, acetaminophen is oxidized via the hepatic cytochrome P450 enzyme system. Metabolic oxidation via cytochrome P2E1 produces a toxic metabolite, N-acetyl P-benzoquinone, otherwise known as NAPQI, which is highly reactive. The molecule has been oxidized and therefore losing the protons off the nitrogen and oxygen and creating a double bond between each of the atoms and their alpha carbons. This toxic metabolite then undergoes glutathione conjugation followed by further metabolism that generates a water-soluble mercaptic acid derivative which is then excreted in the urine. The toxicity of acetaminophen is due to this NAPQI, not acetaminophen itself nor any other major metabolites. Studies suggest that cytochrome P3A4 and cytochrome P2E1 are the primary cytochrome P450 isozymes responsible for the generation of toxic metabolites. Accumulation of NAPQI may occur if primary metabolitic pathways are saturated. The conjugates that are formed through glucuronidation and sulfation of acetaminophen undergo excretion through the kidneys. Glucuronidation is again the main metabolic pathway in which acetaminophen is eliminated from the body. At therapeutic doses, NAPQI reacts with the sulfohydryl group of glutathione to produce a non-toxic conjugate that is also excreted by the kidneys. At higher doses and accelerated concentrations, it is difficult for all of the toxic metabolite to be excreted. The target cell for acetaminophen and NAPQI are the hepatocytes. The hepatocytes are a major component in the main tissue of the liver, and they are approximately 70 to 85% of the liver's cytoplasmic mass. Within the hepatocytes, smooth endoplasmic reticulum is an abundant organelle, whereas most cells in the body have small amounts of smooth ER. Also, the hepatocytes contain many detoxifying enzymes. The hepatocytes' major functions are carbohydrate, protein, and fat metabolism, and they are well known for synthesizing most plasma membranes, such as albumin. The hepatocytes play a critical role in oxidizing, synthesizing, and removing compounds that are being absorbed in the body, and are a host of various metabolitic reactions. Therefore, healthy hepatocytes play a major role in normal physiology. The maximum daily dose of acetaminophen is 4 grams. Liver failure has been observed at doses as low as 6 grams per day. Typically, therapeutic doses of acetaminophen are not hepatotoxic because most of the acetaminophen gets glucuronidated or sulfated with little bioactivation. High doses of acetaminophen may cause glutathione depletion, accumulation of NAPQI, and produces a hepatic necrosis, which is an uncontrolled or unprogrammed cell death that can be fatal. The source of this toxicity in high doses involves free radicals, either reactive oxygen species or reactive nitrogen species that are byproducts from our body's normal functions. But once reactions are uncontrolled and delocalized, they can help activate acetaminophen nephrotoxicity. The important function of glutathione as a radical scavenger is compromised by an overdose of acetaminophen because of glutathione depletion. Experimental observations suggest that bioactivation of NAPQI and glutathione depletion prime hepatocytes for cytokines released by activated Kupffer cells. The exchange of signals between toxicant-primed and activated Kupffer cells is likely a factor in the acute hepatotoxicity produced by many compounds that damage hepatocytes. Therefore, agents that activate Kupffer cells accelerate the toxicity of acetaminophen. This mechanism of toxicity can be explained through a complex sequence of steps. The first step involves cytochrome P metabolism to a reactive metabolite which depletes glutathione and covalently binds to proteins. Step 2 involves the loss of glutathione with an increased formation of reactive oxygen and reactive nitrogen species within the hepatocytes, and the formation of covalent adducts with the hepatic proteins. Step 3 involves increased oxidative stress associated with alterations in calcium homeostases and initiation of signal transduction responses causing mitochondrial permeability transition. Mitochondrial permeability transition occurring with oxidative stress is step 4, leading to the loss of mitochondrial membrane potential and loss of the ability of the mitochondria to synthesize ATP. Lastly, step 5 is the loss of ATP, which leads to necrosis. The oral LD50 for rats for acetaminophen is 1,944 milligrams per kilogram. Overdoses are easy to induce and can take some time to be recognizable. The acute signs of liver damage caused by an overdose of acetaminophen may include nausea, vomiting, stomach pain, loss of appetite, increased sweating, and fever. Acetaminophen is therapeutic in the basis that it is thought to act primarily in the central nervous system, increasing the pain threshold by inhibiting both isoforms of cycloogenase 1, 2, and 3. If untreated, an overdose of acetaminophen can lead to liver failure and death within a few days. Early intervention can prevent irreversible liver damage that consists of treatment with N-acetylcysteine. N-acetylcysteine acts as an antidote by delivering to the liver a high concentration of cysteine, therefore replenishing glutathione levels.